As one journeys to the center of the Earth, temperatures warm 17 degrees to 30 degrees Celsius for every kilometer in depth and reach 5,100 degrees Celsius in their inner core, nearly the temperature of the Sun. The energy that heats Earth's interior derives from several sources. First and foremost is the decay of radioactive isotopes, particularly 238 uranium, 235 uranium, 232 thorium, and 40 potassium. Net heat flow from the interior of the planet to the surface amounts for about 30 million megawatts. For perspective, this is only 0.03% of the energy that the Earth's surface receives from the Sun. Earth's crust varies in thickness from about 5 to 75 kilometers. Locations where the crust is thinner, such as at the boundaries of tectonic plates, fault lines, and volcanoes, receive more heat from the interior and thus are promising sites for geothermal power. For example, California, which lies at the intersect between the Pacific and North American plates, is home to more geothermal power plants than anywhere else on Earth, and they supply the state with over 7% of its electricity. A geothermal power plant pumps water down a deep injection well. As this water flows through fractures in the fiery brimstone, it heats up until it escapes up a second borehole, the production well. In the power plant, steam from the production well drives a turbine. A condenser and cooling tower lower the temperature of the water before it returns back down the injection well. Boreholes for the wells are lined near the top to prevent water from penetrating through porous rock. A makeup tank replenishes the water lost during its passage through the system. Today, most commercial geothermal wells are shallower than 3 kilometers. Deeper wells reach higher temperatures and thus generate more power, but drilling becomes prohibitively expensive. The petroleum industry is developing more economical methods for drilling oil or gas wells 6 to 10 kilometers deep. Transfer of this technology should soon reduce the cost of constructing deeper, hotter geothermal wells. Geothermal electric power plants have many advantages. They are economical, and California geothermal plants cost less than most other types of power plants. They have the potential for expansion. Geothermal plants could provide 1/4 of the electricity in the United States by 2030 at a reasonable price. They provide power day and night, be it windy or calm, come rain, come shine. They discharge much lower amounts of carbon dioxide, nitrogen or sulfur oxides, and particulates than fossil fuel power plants. Disadvantages of geothermal power are severalfold. Sites suitable for geothermal power are often far from population centers. For example, the east coast of the United States has limited possibilities for geothermal power. Injection of water into wells could compromise the stability of surrounding geological formations, but based on substantial evidence collected so far, the probability of inducing damaging seismic activity is low. Sailors and surfers can attest to the power of the sea. Tides rise and fall from the interplay between Earth's rotation and the gravitational forces of the Sun and Moon. Waves develop from the pressure and friction of winds blowing over the open seas. Humans have a long history of harnessing tidal and wave power. The ruins of a tide mill used for grinding grain on Stratford Lough in Northern Ireland date to 619 AD. On a larger scale, a tidal power plant on the Rance River in northwest France has generated 600 gigawatts per hour annually since 1967.
In terms of the tidal energy is the marine equivalent of wind energy. And you know that if you run your hand through the wind, there's a wee bit of resistance, but if you run your hand through water, there's much more resistance. So with a current flowing in the water, there's a lot more energy in there. And so it really is just the equivalent of wind energy, and you can see that with a lot of the turbine designs that people are looking at. They really look like big windmills. But of course, because there's so much energy there, because of the density of the water, you don't need the same speeds. And just as the wind flow over hills and things is quite turbulent and people are used to that, so the actual flow of tidal energy is very turbulent as well. And so when people think it's very smooth, that isn't the case. So things have to be designed to take that turbulence into account.
Tidal and wave power are the least common forms of renewable energy. To date, only 3 tidal and no wave power plants are in commercial operation. Costs for these sources are not yet competitive with others because of the expensive equipment that works reliably under constant buffering of the sea and that withstands saltwater corrosion. In summary, number 1, photovoltaic and solar thermal electricity generation are advancing in efficiency, but are still more expensive than most other types. Number 2, In the right location, a geothermal power plant costs less than other types and produces clean energy continuously. Number 3, tidal and wave power are the least common forms of renewable energy and are not yet cost competitive.